Okay, so today we're going to talk about a bunch of different stuff, um, but mainly all the things that have to do with functions. Um, First thing you want to know is about domain and range of a function. The domain of a function is what x is allowed to be. Um, Now, there are several things that affect domain, but the two most common things that you will see affect domain are going to be one, um, dividing by 0. You're not allowed to do this, okay? So for an example, if you had a function that's like 1 over x, at this point, x could not be 0. So that's limiting your domain because you're not allowed to divide by 0. Um, your second thing that you will mainly see is square root, or excuse me, not just square, but an even root of a negative. Okay, so this, as an example, would be like f of x equaling the square root of x. In this case, x cannot be less than 0. So, or what you might say is that x has to be greater than or equal to 0. So this is limiting your domain. You no longer have access for your function to numbers that are less than 0. Your range is going to be what y can be, right? So this is all based off of the inputs that you have. What can your inputs do for you? So this is going to vary based on what type of function you're looking at, what's happening to it. So this is a lot more complicated to kind of grasp, but you really have to pay attention to what type of function you have, and we'll go on into detail later as to what can and cannot happen. But for example, like a square root can't create a negative number, so in that case, your range would only be positive numbers, and so on and so forth. So range is a little more complicated to tell, but that's what range is. Mainly focus on your domain. So if we look at what is a function and what is not a function, a function is anything that where you have one you have only one output per input. So, um, for example, if I did f of 1, and let's say I got out a number 5, if I was ever able to plug 1 in again and get 6, then I don't not a function. This is not. It would always have to be 5 in order for it to be a function. I cannot have multiple outputs for the same input. You will see this, mainly visually as something like a circle. So a circle, if I input the number, let's just call this 1. If I inputted 1, I would have two different options to pick from, right? Because I'm either going to be some negative value or some positive value. Well, this isn't a function. You don't normally hear about this in algebra as the vertical line test. If if I can at any point in time draw a vertical line that touches my function twice, we are no longer a function. So that's the definition of a function. One input, two output. Or, no, one input for one output. Okay, so the cycle of polynomials, this is a very, very important concept to understand. And this is all dependent on degrees. And you can think of this as like even versus odd. So this isn't symmetry necessarily, but even versus odd degrees. So let me explain what I mean. So let me draw a set of axes here. So we've got 1, 2, 3, and 4. So we're going to say that this is x to the 0, or just some number. So like, it's just some constant, c. So like, for example, like y equals 2, something like that. All right, so you just have some number. Well, that number is going to just be a flat line. Okay, this is important. Notice that the symmetry here is perfect, right? It's even across the line. You're starting and ending roughly going in the same direction. Your next one is going to be x to the first. So this is some sort of line. A line is going to start and end in different areas, right? We start negative and end positive. Okay? Now, this pattern is going to hold. We're going to skip evens, go with evens, odds go with odds, and they behave very similarly. Um, so the next one is an x squared. So this is like a parabola. Notice how it's, again, very symmetric. It starts up high and it ends up high. It could obviously do the opposite and start low and end low, but that's how a parabola would behave. And we look at this degree of our polynomial. When we go to x cubed is going to behave more like a line. Now it looks different, but overall that's what it behaves like. It starts and ends going in those same directions. So that's a good concept to understand, that as you go from a degree of 0, or just like a regular constant, that behaves this way, that's also how an x squared function is going to behave, and an x squared function is how an x to the fourth function is going to behave, and so on. Same thing for odd functions. If you start off with x to the first, it's going to behave very similarly to x cubed, which is going to behave very similarly to x to the fifth, and so on. So I'm going to erase these real quick, and we are going to switch to kind of the reciprocals of these, and you'll see that it actually behaves very, very similarly. So again, we start off, we'll leave this line here for x to the 0. Well, let's say we go x to the negative 1, or 1 over x. So how does this behave? X to the negative 1 is going to look like this. Okay? So like, we still have this kind of symmetry where we're kind of cutting across the graph instead of being symmetric across the y. Now, when we go to x to the negative 2, that is going to, because we are squaring, even though we are now in the denominator, because we're squaring, we end up with this similar type of graph, but we always have to be positive, right? We're positive over time. That's what that's going to look like. And then we end up going to, x to the negative 3, which is 1 over x cubed. That is going to look very similar to the other ones. It's going to be a little more tight at times, but overall, this is the way that the graphs are going to look. So kind of just generally understanding what it is that you can expect from the graph can really help us understand it over time. So we've got some special functions. Our first special function is going to be the absolute value function. The absolute value function is basically a hard V. Now this can be moved around everywhere, but it is a line generally, and this is the absolute value of x. This is a line generally that could be moved, it depends, but it changes to a different line at a particular point. Another function is going to be a square root function, so square root of x. Now, square root of x, that is a function, again, when we looked at our domain, we're not allowed to be negative. So it is almost like a parabola, except sideways, right? So if you can imagine that it goes down in this direction as well, although we're not allowed to be negative, so that's why we don't have that part. But that is going to be, again, kind of how that looks. Now, if we have a cube root looks just like a cube root is allowed to be negative because you can take a negative times a negative to make a negative. So it's going to look like a cubic function, but just kind of inverted a little bit. So it looks like this. So pretty similar to a square root. I mean, it's going to be a little bit shallower, but it can be negative. So its domain is not limited. And then we move on. And we're going to have two functions. I'm going to draw them together, different colors. We're going to have the cosine of x. Cosine always starts off at 1 and then dips. So that distinguishes it from its kind of partner, which is sine of x. Sine of x starts at 0 and goes up, right? So those graphs kind of, they go back and forth, obviously, between 1 and negative 1, but the main thing is that cosine starts at 1 and sine starts at 0. It's the big difference between the two of those. Okay, so transformations now. Transformations, lots of different transformations can happen. So I'm going to draw this really big. So we've got, or well, maybe not. So we've got our function f of x. We can do lots of different things to this. So we could do f of x plus b, some number b. That is going to be, it's going to shift b left. Okay, so a lot of people always want to move this right because you're adding. But the way I think about it is that you are adding a number to x. So you're allowing x to be smaller than it would normally be in your graph. So that's why it shifts everything to the left, because x can now be smaller than it was before to get to the same place. You can have f of x minus b, which is going to shift b right. So that is, again, so you're taking away from x. So now what you're doing is you're forcing x to be larger than it would normally have to be. So it makes all the points in the graph move further to the right to where they would be before. You can have f of x plus c, which is shift c up. Now this is basically you're taking the same graph, but you're adding some number to it. So every point, it'll be in the same on the same x, but it's just going to be up that many extra units. You have f of x minus c, which that is going to be shift c down. So that's one thing. Now, really the last transformation that we will mainly see, and there are some other ones, is going to be negative f of x. So if I were, what happens if I were to just take my function and make it negative? Well, this reflects over the x-axis. So this is just going to flip my graph completely. It's going to turn all my positive y's into negatives and all my negatives into positives. And that's why it reflects itself over the x-axis. So composite functions. So if we have two functions, normally you have, and I'll do an example of this real quick. So let's say I have f of x, and I define f of x to be x squared. And then I have g of x. I'm going to call this the square root of x. Okay? Well, what composite functions do is you're going to take an input and think about it more so that whatever I plug in to f, so just, I like thinking about it as boxes because sometimes x's get confusing, is that what I'm doing is I'm squaring whatever I input. And g says whatever I input in, I have to take the square root of that input. So it doesn't matter what you plug in, you're squaring it. That's what this says. For every x, I square that. For everything here, I take the square root of it. So if we look back up at the top, if I were to do f of g of x, g of x is the output. That is this. That is the square root of x. It is the same. That's what equal sign means. It's the same. So I'm going to replace that with the square root of x. Well, it tells me right here that whatever I plug in, I have to square. So I'm going to get the square root of x squared, which gives me x. That's not surprising because these two functions are actually inverses of each other. They undo the other in a sense, and then you get back to your original input. So like g of f of x. Now I need to take f of x, which is the same thing as x squared, because again they're equal to each other. So I'm going to get g of f of x, and this is going to become the square, or this is going to become, sorry, the square root of x squared, which again we all know is x. So this in fact proves that they are inverses of each other, because if we do composites of them, we end up getting x as our answer. And lastly, we're talking about this even versus odd thing. You saw this earlier. Even is the same thing as y symmetry, which we have been discussing. That means that if I plug in a negative x into my f, I get the same f of x back. And you have odd symmetry is the same thing as origin symmetry, which is if I plug in an opposite of x, I get the opposite f. So this just flips my graph. So, a quick example, from each, an example here would be f of x is x squared. And you can see that with the graph of x squared, same thing is happening to the left and the right. And an example of odd symmetry would be x cubed. Because for every negative x I plug in, I get the opposite of what I would have if I plugged in the regular version.